Now we'll apply the fully developed region definitions to those equations and see if we can get it down simplified into something that we can actually solve. So we're going to start with the fact that the velocities do not change in the z direction. So that's going to be d by dz of vr and vz and v theta are all going to equal 0. In addition, we've already said that v theta is going to equal 0, so we're assuming no swirling flow. Flow is just going straight down the pipe. And that there are going to be no gradients in the theta direction because there's no reason to think that anything will be changing as you circle the pipe. We're going to define the radius of the pipe to be big R0 here, just for convenience. And of course, the flow is going in the fully developed region is steady flow. So that is no time dependence, no time derivatives. If we're looking at the conservation of mass equation in cylindrical coordinates for incompressible steady flow, we have this equation, and v theta we said is 0, so we can kill this term, and the derivative with respect to z is 0, so we can kill this term. So we're left only with these two terms equal to 0, and the question is, what can we conclude from that? And you really can't conclude much from that just looking at them in this form, and this is one of the trickier things about cylindrical coordinates. It comes up a lot. If you look at this like this, I would say that you could say you don't really know what that has to tell you about the flow. But we can change that, and we can look at it as this. So take a minute and stare at this and convince yourself that this is the same thing. So it's really saying that this is true. They're both true, but this is a different form of this same thing. So if you take this derivative, you get this. You get these two terms due to the product rule. We can, actually that's not quite true. If we do that, it's now true. So that's what this is saying. And of course we can multiply that by r, and we get what the equation that I want to stare at. So we say, all right, if that's true, then this has to be true. So this group right here has to be equal to 0. That is the derivative of r times vr is equal to 0, which means that group does not change as you change r. So if we know the value of this group together at any point in R, we know the value of this group at every point in R. And that, of course, we do know one of the values of this point at a particular position. We know that at R equals 0, at R equals R, sorry, R naught, at R equal to R naught, we know that VR is equal to 0. Because that is the pipe wall. So we know that this grouping is 0 at the pipe wall, and therefore we know this grouping is 0 at all positions R, because it does not change in the direction of R. And obviously R changes, so the only way that this can remain 0 is if VR is equal to 0 at all R. So that's our punchline from the conservation of mass equation, that there is no radial velocity. So there is no theta velocity and there is no radial velocity. Now we'll go back and look at the radial velocity equation and see if anything is left out of that. So the radial velocity equation, of course, is quite lengthy, as we already saw. It's rho dvr dt plus vr dvr dr plus v theta over r dvr d theta minus v theta squared over r plus vz dvr dz. And then on the right hand side we have minus dpdr, and we have the viscosity, and then we have d squared vr dr squared plus 1 over r dvr dr minus vr over r squared plus 1 over r squared d squared vr d theta squared minus 2 over r squared times dv theta, sorry, that's not very well written, dv theta d theta plus d squared vr dz squared. But we now know that vr, well, first of all, it's steady state, so we kill that. Vr we just said was 0. V theta and vr is 0, we kill that. V theta is 0, we kill that. d by dz is 0, so we kill that. dpdr can stay, d squared vr, well, vr is 0, vr is 0, vr is 0, vr is 0, v theta is 0, vr is 0. All right, so we get the expected result here, dpdr is equal to 0. So there's no pressure difference in the radial direction either, which means that P is only a function of Z. So that's, of course, going to be the same useful result that we got in the in-between plate analysis. We're going to see, of course, that that's going to be very important for ultimately solving the situation, which we will get to now. So the next thing we want to do is look at the Z momentum equation. So the R momentum equation gave us this. The mass conservation equation gave us the fact that VR is equal to 0. Now we'll take a look at the Z momentum equation. As I say, that's the direction where things are actually happening. So rho dvz dt plus VR dvz dr plus v theta over r dvz d theta plus vz dvz dz. And then we have minus dp dz, and then the second derivative terms for the viscosity, d squared vz dr squared plus 1 over r dvz dr plus 1 over r squared dvz squared d theta squared, d squared vz d theta squared, and finally d squared vz dz squared. All right. Again, a lot of these are going to go away. Steady state, VR is 0, that one's gone. V theta is 0, that one's gone. dvzz, well, dz, anything by dz is 0. Things aren't changing in the z direction. That one's gone. dvz dr squared, all right, well, that's not gone. 1 over r dvz dr is not gone. dvz d theta, well, anything with the d theta in it is gone. Derivatives in theta direction are gone. And derivatives with z direction of velocity are also gone. So we're left with two terms. This, of course, should remind you very strongly of flow between a plate because we were left with the same types of terms. This is now our new equation, mu d squared vz dr squared plus 1 over r dvz dr. So we have only viscosity and pressure in the z direction, velocity and pressure gradient in the z direction. That's going to be our equation. And of course, next class, next lecture, hopefully you have anticipated what's going to happen next. We are going to be able to integrate these.